and welcome to my presentation on freshwater conservation planning in an intact boreal landscape. My name is Meg Southee, and I am the GIS Analyst and Spatial Data Manager for the Ontario Northern Boreal Program at Wildlife Conservation Society Canada. WCS Canada is a not-for-profit conservation organization that does boots-on-the-ground field research in large intact landscapes in Canada. We work with a variety of species at risk, including wolverine, caribou, and lake sturgeon, and we provide independent scientific research to support land use and policy decisions to protect Canada's wildlife and wild places. In this presentation, I will go through the intro, methods, results, and discussion of our most recent scientific analysis on freshwater conservation planning in the far north of Ontario. The focus of this presentation is on identifying important habitat for 30 species of freshwater fish and 4 focal species: brook trout, walleye, whitefish, and lake sturgeon. Inland waters and freshwater ecosystems have some of the highest rates of biodiversity loss, and these losses have been accelerating since the 1970s. Consequently, freshwater species are among the most imperiled, with an 84% decline in global freshwater vertebrate populations, as compared to a 40% decline for terrestrial vertebrates and a 35% decline for marine vertebrates. In response to the Aichi targets formulated at the Convention on Biological Diversity, Canada set conservation targets to protect 17% of its terrestrial and freshwater areas by 2020 and 30% by 2030. More recently, it has announced a new target of 25% protection by 2025. Systematic conservation planning uses spatial optimization to generate conservation solutions by evaluating trade-offs between a set of decision variables to meet explicit targets. This approach is widely accepted as an effective method to identify areas for biodiversity conservation. However, it has only recently been applied in the context of freshwater. In this study, we examined different prioritization scenarios to conserve freshwater species while avoiding areas with high human disturbance and including freshwater connectivity. Conservation planning rarely includes explicit freshwater objectives or considers the unique characteristics of freshwater systems. Protected areas designed for terrestrial habitats or species may not adequately address the connectivity of freshwater systems, where impacts in headwaters can affect downstream habitats that are located hundreds of kilometers away, and where changes to water flow through damming and water extraction can greatly alter the characteristics and habitats in freshwater networks. We developed 3 research questions to identify important areas for freshwater biodiversity in line with Canada's existing conservation targets. We also examined how well the biodiversity solutions align with the habitat needs of 4 focal species, and how well the existing protected area network addresses the needs of freshwater species. Our study area is the Arctic Area Drainage Basin in Ontario, Canada. This area is over 700,000 kilometers squared, which is more than 170 million acres. It includes 9 major river basins, thousands of lakes, and some of the few remaining undammed, free-flowing rivers in the world. Rivers flow from south to north in this landscape. The largest wetland complex in North America is located here along the shores of Hudson Bay, and it is one of the most productive subarctic coastal wetland habitats in the world. Ecologically, there are at least 50 species of native freshwater fish in this area, a limited number of invasive species and pathogens, and low human impacts compared to other subarctic regions in Canada. Socially, freshwater fishes are highly valued by First Nations and local communities, where they are critical components of food security and food sovereignty, as well as important for livelihoods through recreational and commercial fisheries. This area is divided into 2 management regimes: the Far North Planning Area, which is some of the last remaining intact boreal forest, and the southern area of undertaking, where there is active commercial forestry and other large industrial disturbances like mining, hydropower, transmission corridors, and all-season roads. The Far North Planning Area is home to over 30 remote fly-in First Nation communities that are accessible by ice roads in the winter and by airplane in all other seasons. This area has minimal industrial disturbance, but there is increased interest in development projects, especially in the area known as the Ring of Fire, a crescent-shaped band of mineralization with large deposits of chromium, copper, and nickel that are buried deep beneath the muskeg and peatland that pervade this freshwater-dominated landscape. We focused on the 30 most common native freshwater fish species in the study area, including the 4 focal species seen here. The focal species were selected because they are representatives of the major fish community guilds and important landscape species. Additionally, lake sturgeon is designated a species at risk at the provincial, federal, and international level, and it is a culturally important species for local indigenous peoples. We use the 30 native species as a measure of overall native freshwater fish biodiversity. Our methods are divided into 3 parts: species distribution modeling, development of a cost variable based on human disturbances known to affect freshwater fish species, and running the conservation prioritization scenarios. We generated watershed planning units from 6 30-meter hydrology and forest enhanced flow direction grids available from the Ontario Ministry of Natural Resources and Forestry. We used a threshold of 300 kilometers squared to create a drainage network based on modeled overland flow, resulting in 1,417 stream segments and corresponding watersheds with an average area of 500 kilometers squared. This processing was completed using the ArcHydro toolset. We then compiled freshwater species occurrence records from 4 publicly available datasets and used climate and biophysical datasets to develop species distribution models. Variable choice was informed by selecting variables that are ecologically meaningful for fish, describe unique aspects of the habitat suitability, and avoid collinearity. Using maximum entropy distribution modeling, or MaxEnt, we generated species distribution probabilities for the 30 native freshwater fish species with values that vary from 0 to 1 across the study area. We attributed the mean probability for each species to each watershed planning unit, and used these values as the species representation targets in the conservation prioritization analyses. To model connectivity between the watershed planning units, we calculated the longitudinal distance between each pair of connected watersheds and used the inverse distance between planning units as a connectivity penalty when selecting watersheds in the conservation prioritizations. For the cost variable, we developed an anthropogenic impacts index based on a principal components analysis of 11 human disturbances known to impact fish. The first principal component from the PCA captured 28.8% of the variation among the watershed planning units, and a broken stick analysis determined it was the only meaningful component. This component was assigned to each watershed and used as the cost in the conservation prioritizations. We ran 12 different prioritization scenarios to meet the 2 area-based targets. We examined 2 biodiversity scenarios, one where we locked in the existing protected areas, or the seeded analysis, and an unseeded analysis that had no constraints. The biodiversity scenarios used the species representation values for all 30 species. We also ran unseeded scenarios for each of the 4 focal species independently. The conservation prioritizations were run using Prioritizer, an open source R package in the Gurobi solver. Prioritizer uses integer linear programming to find the true optimal solution and is more computationally efficient than heuristic methods like Marksan. We solved a minimum set problem for a range of species representation targets, from 10 to 90% in each scenario, to find the solution that covered 17% and 30% of the landscape, respectively. With respect to our first research question, what watersheds are selected to meet the 17 and 30% area-based targets while maximizing freshwater fish biodiversity, we found that there were 47 watersheds consistently selected to meet the 17% target, covering 3.7% of the study area. You can see these on the left. Likewise, there were 190 watersheds, shown on the right, that cover 13.9% of the study area and were consistently selected to meet the 30% target. The selected areas included headwater planning units, tributaries to large rivers, coastal planning units, and watersheds with limited or no upstream human disturbance. Specifically, the Kapuskasau River and sections of the Albany River Basin were important at the 17% target, while watersheds in the Severn, Winnisk, Attawapiskat, and Albany River basins were important at the 30% target. When comparing how well the 4 focal species are represented in scenarios that prioritize biodiversity and vice versa, we found that the biodiversity solutions performed well for habitat generalists, like whitefish and walleye. Brook trout, a habitat specialist, was the least represented in the biodiversity solutions and performed the best when it was prioritized on its own, with 24% and 36% of its habitat represented at each of the two area-based targets. Lake sturgeon had mixed results, where it performed better on its own at the 17% target, but at the 30% target, more of its habitat was represented in the unseeded biodiversity analysis. For our last research question, we examined how well the existing protected areas support freshwater fish species. For this result, we found that a larger number of protected areas watersheds were selected in the unseeded biodiversity solution than in the focal species solutions. Seen here, there is little to no selection of the existing protected areas in the south and southwest portion of the study area in the 4 focal species solutions, but there is a high selection of the protected areas in the Ekwan and Winix basins. These northern watersheds are important as climate refugia, as warming waters will push species further north, and they are more intact than the southern watersheds that have already been disturbed by commercial forestry and other industrial activities. In conclusion, we found that despite the high species richness in the southern watersheds, these areas were only selected in the biodiversity solutions and were not selected in the focal species solutions. Our results suggest that by attempting to meet the needs of a diverse community of fishes, there is a risk of limiting the selection of specialized areas for a given focal species like brook trout. Lake sturgeon is both a cultural keystone species and a species at risk, and as such, it is important to consider its habitat needs in any watershed and regional conservation planning process. Lastly, the species distribution probabilities for the 4 focal species were higher when the prioritizations were not constrained, suggesting that there are additional areas not captured in the existing protected areas network where the conservation outcomes for these focal species can be maximized. Thank you for watching my presentation. If you have any questions, please don't hesitate to get in touch. Have a good day.